Hello, welcome to this lesson of the Linear Algebra Tutor, volume number 2. Here in this set of lessons, we're going to expand all of your skills in linear algebra, building upon everything that we've learned in volume 1 of the Linear Algebra Tutor. So at this point, I want to say up front, if you have not watched those lessons in volume 1 of linear algebra, then you really need to stop now, go back and watch all of those lessons, because linear algebra, just like all math classes, it builds, every skill builds upon the last one. So I'll be talking about some things here. If you don't know what I'm talking about, then you'll be lost. But none of this stuff is hard, so make sure you've watched that before. I'll do a real quick recap. What we have covered in Linear Algebra Volume 1 is the concept of a matrix. The concept of vectors can be represented as column matrices. We've talked about the dot product of vectors in terms of matrix algebra. We've talked about how to multiply matrices together by one another. We've also talked about a lot of properties of matrices, and then we moved into a whole discussion about how to solve systems of equations using matrices, and we talked about those row methods, the row reduction methods, how to transform a matrix and simplify it into a different looking form, but yet represent the same system of equations, the same matrix information is there. We do the row reduction techniques for that. And then we concluded the last volume with the concept of the inverse of a matrix, and we showed you how to calculate the inverse, or at least one way how to calculate the inverse. And then we showed you what that was used for, because you can use inverses to solve, again, systems of equations. So that's all very, very relevant material. In this set of lessons, we're going to cover totally different stuff, building upon the last thing. Now, the first thing I want to talk to you about is we're going to talk about what we call the transformation matrices. Very simple concept. Basically, what you want to do a lot of times is you want to take a point in XY space, a point on the XY plane, and you want to transform it in some way. You might want to scale it, make it bigger or smaller, or you might want to move it around or something. And so when you're talking about transformation matrices, it makes a lot of sense to start thinking about a computer screen. So when we talk about this, I want you to picture this being a computer screen, two-dimensional computer screen, X and Y, and we want to take a point, a single point on that, and we want to do things to it, right? So you might think of computer graphics. You know, you might have a shape, a triangle on the screen. You might rotate the triangle, you may shift the triangle up, you might make the triangle bigger or smaller. Well, that triangle consists of a bunch of points on the screen, pixels on the screen. So every point in the triangle has to be dealt with, either scaled or rotated or translated, in order to move that shape around. So if I have a shape on the screen, like this marker could be a rectangle or something, and I want to move it over here, I'm doing a translation here, I'm doing a rotation, and I'm also doing, maybe I could be making it bigger or smaller. That's called scaling. So when I move things around like graphics on a screen, you're doing all of that stuff at the same time. And of course, in 3 dimensions, it's the same math holds, it's just extended somewhat. So here we're going to break it down. We're going to talk about scaling, which just means making something bigger or smaller. So let's think about that and think about a two-dimensional object on a computer screen. Let's first talk about scaling in the X direction. So in other words, if I have an object, I want to stretch it out horizontally first. We're going to break it down into that. So there's what we call a transformation matrix associated with scaling in the X direction. And that transformation matrix, I'm going to call it A. And that transformation matrix is called K, 0, 0, 1. Now, 0 and 1 are just numbers. Those are just regular numbers. K is what you call your scaling coefficient. So if you want to make something bigger by 2 in the X direction, then K would be 2, because you're doubling everything. If you want to make it 5 times bigger in the X direction, then K would be 5. If you wanted to cut it in half, maybe shrink the size of whatever it is in the X direction, K would be 1/2. So K is just a number. It's telling you how much scaling you want to do in the X direction. Now, we're thinking of this in terms of a computer screen, which is, shapes, stars and triangles and rectangles. But you really need to kind of think about that every object on a computer screen, it consists of lots and lots of points. We call them pixels when we talk about computers. So to demonstrate and to talk about scaling, we are going to talk about the individual points. So we say K is scale. Of course, only in the X direction, because that's what we're talking about. All right, so let's do ourselves a favor here, and let's draw a couple of points that we're going to be of interest here. We're going to be using these points a lot in this whole discussion. So let's say here is an X, y plane, and this is 1, this is 2, and this is 1. We're going to choose some easy points, all right? So we're going to have one point located at the intersection of 1, 1, and we're going to have another point at the intersection of 2, 1. And just to kind of remind you, even though I know you know how to read, this is 1, 1, and this is 2, 1. So here's a point here, here's a point here. All right, but you got to also realize that we're just talking about 2 points here, and we're going to be scaling these points in the x direction, right? But the reason we're doing this is because you end up applying the whole thing to two-dimensional shapes on a computer screen. And so you're applying the same transformation to everything inside of the object. All right, so in order to pull this transformation off, the way that you do all of these things is the new point is called x prime. We're basically going to be transforming and scaling these 2 points in the x direction using this matrix. The original points are called x, x1, x2 if you want to call it that. The new point, we put a prime on it. That means we've done the transformation, we've scaled it. So the new point is going to be equal to the transformation matrix times the point. But notice that these points have 2 numbers associated with it, x, y, and we've already talked in matrix algebra or in linear algebra volume 1 that any point can be represented as a column vector. Basically, when you think about it, this point is a point in 2-dimensional space, but you can imagine a vector going from the origin and pointing to this point, and you can imagine a vector going from here to here. So the bottom line is, and I'll just switch colors so you can see it very clearly here. The bottom line is that A is our transformation matrix, right? So what we're going to have is K, 0, 0, 1. And in this case, our first point is this guy right here, 1, 1. So we represent that as 1, 1. Now we haven't actually put a value in for K yet because we just haven't talked about it yet. So let's talk about a specific case. Let's say how much do we want to actually scale this thing in the x direction. So let's say we double in the x direction. If this were a triangle, that means you would be stretching it out multiplied times 2 in the x direction, but here we just have 2 individual points here. So in order to do that, what we say is the new point is going to be the transformation matrix times the original point, and what it's going to be is, since we're doubling it, k is going to be 2, so we'll have 2, 0, 0, 1, and then one of the original points we have here is 1, 1. So what would this point be? Now you have to turn to your matrix methods. This is just a matrix multiplied by another column matrix. Okay? So you go over and down. And I'll switch colors here. And what you have here, 2 times 1 is 2, right? Plus 0 times 1 is 0. So you just get a 2 up here. And then go to the next line. 0 times 1 is 0, plus 1 times 1 is 1. So you have a 1 right there. Okay? So what we have done is we found out that if we take the original point, we scale it by 2, we get a new point. That's 2, 1. Notice what's happened. The original point was at 1, 1. Now the new point is 2, 1. We have stretched it out in the x direction times 2, but the y direction has remained unchanged. We haven't done anything to it. That comes about because of the way this transformation matrix is set up. Because the scaling coefficient is only in the top row on the left, it's only going to affect the x direction. And the way that matrix multiplication works is you're not going to touch the y. So let's do this for the second point. Okay, for the second point, I'll go ahead and change this color here. The second point is we have 2 points on our little graph up there. Let's do the second one here. The same transformation matrix holds, 2, 0, 0, 1. Now the second point that we have is 2, 1. So we'll put 2 and 1 here. This represents the point, and we're going to scale this point again with the same matrix. So what we're going to get over here is we go over and down. 2 times 2 is 4, plus 0 times 1 is 0. So we get a 4. And then 0 times 2 is 0, plus 1 times 1 gives us 1. So notice what happens here. The point 2, 1 becomes 4, 1. So we have stretched it times 2 in the x direction. The y direction has remained unchanged. All right? And I think that you can see that if you would do that, I'm not going to draw them for every single one, but we'll do it for this first one since it's, you know, just our first little example here. We'll put a couple of tick marks here on the x direction like this, and we'll put some tick marks in the y direction like this. The original 2 points was 1, 1, which is right here, and 2, 1, which is right here. So we'll call that x1 and x2. The new points are at 2, 1. That's what the first point transformed to. That's right on top of this. You can see that we've stretched this times 2. The next point is 4, 1. Here's 4, 1 right here. So this will be x2 prime. x1 prime, 2, 1 falls right on top of this point, so I really can't draw it here. But you can see how x2 has stretched horizontally times 2. x1 has also stretched horizontally by 2, but we've again affected nothing in the y direction. So again, these are just 2 points, but imagine a shape consisting of 1,000 points in 2 dimensions. It will all be stretched horizontally. So that's how you apply, in general, the scaling matrix in the x direction. Now that you have the concept of a scaling matrix, now we can talk a little bit quicker about some of the other scaling matrices out there. What if we want to only scale it in the y direction? Only in the y direction, okay? So what's the transformation matrix for that? Well, it's going to look similar. The transformation matrix will be 1, 0, 0, k. Notice now the scaling coefficient is down in the lower right. Okay, that's going to end up affecting only the y components of all the points. The 1 is up here. That means x is going to be left alone. So let's just say that you want to, let's say that you want to multiply by 3 in the y direction, right, in the y direction. And let's go ahead and say that we have a couple of original points here, over here, x, y. Let's go ahead and talk about our original points. 1, 2, 1, 2, 3, 4. We'll put these guys here. The original points we say 1, 1 and 2, 1. So we'll call this x1. We'll call this x2. So again, it's 1, 1 and 2, 1. Those are my original points. We want to transform those according to the scale, and we're multiplying by 3 here. So what we have here is the new point is going to be the transformation matrix times the old point. Right? The transformation matrix is 1, 0, 0, and now k is 3 because we want to stretch in the y direction. All right? Now we have to multiply by the original point. One of the original points is 1, 1, so we have that the same as we have before. And then whenever we do this multiplication, what do we get? Well, 1 times 1 is 1, plus 0 times 1 is 0. So we get a 1 up here. Then 0 times 1 is 0, plus 3 times 1 is 3. All right, so what do we get? We take the point 1, 1, and it turns into 1, 3. If we plot that 1, 1, 2, 3, that it goes up here, and this will be x1 prime. So we have taken the x1 point here, and we have stretched it only in the y direction times 3, because that's what we wanted to do in our problem. So the transformation matrix is doing its job. It's scaling it only in the y direction. Now, I don't want you to get confused. We're scaling it in the y direction. Notice I still have x running around here and x running around here. In linear algebra, when you have x, it just means a column vector or a point. So when you see the letter x here, it doesn't mean x component. It means the coordinate pair, x, y. The variable x represents a point in the plane. So you read it as the new transformed point in the xy plane is equal to the transformation matrix times the original point in the xy plane. The variable x represents the pair 1, 1, which is a point in that plane. Also, you can think of it as a vector, which is an arrow pointing to that point. So all of these transformations we're doing with points, they all apply to vectors too, because it's the same math, no matter how you slice it. Now if we want to transform a second point, same way, 1, 0, 0, 3, then we take the second point, 2, 1. The x component goes there, and the y component goes below it. What do we get here? 1 times 2 is 2, 0 times 1 is 0, so we get a 2. 0 times 2 is 2, 3 times 1 is 3. And that's what we get there, 2, 3. So if we wanted to plot that, 2, 1, 2, 3, we get a point here. This is called x2 prime. So notice what's happened with x1 and x2. We have stretched them both vertically. How much? We've multiplied their y components times 3. right? But their x components remain the same. So now we know that we have a transformation matrix that can stretch things in the x direction only, stretch points in the x direction only. And we have a transformation matrix that can stretch points in the y direction only. And that's very useful. You can definitely do those things separately. But it's possible to combine both of these ideas into a transformation matrix that does both of them at the same time, stretch in the x and in the y direction. How do we do that? So if we want to scale in the x and y direction at the same time, if you don't want to do those things sequentially, then the way you handle that is the transformation matrix is the scale in the x direction with a 0, 0 here, and a scale in the y direction. Notice I put subscripts x and y because now you might be scaling in the x direction and scaling in the y direction separately. Like you might stretch two times across, make it twice as big in the x direction, maybe 5 times as tall, right? So if you're scaling proportionally, then these two numbers will be the same, but if you're stretching one way more than the other, they could be different. So let's take an example here. Let's say we want to stretch horizontally by 4, so make it 4 times larger in that direction, and we're going to stretch vertically by 1/2, right? Which really means we're shrinking it, because you know the same math works if you're stretching or shrinking, right? So we want to apply this transformation matrix, and we want to use the same points. So our original points, 1, 1, and then 2, 1. All right, so the new point that we have is going to be the transformation matrix times the original point. That's what this x is right here. The transformation matrix in this case for the x direction is a 4, 0, 0, and the y we're shrinking by 1/2 or stretching by 1/2, which cuts it in half. So that's our transformation matrix. Now the original point that we've been dealing with in all these problems is just 1, 1. So what does the math look like when we do it on 1, 1? Let me take this off and change colors just to make it a little bit easier to read. And what you're going to have is 4 times 1 is 4, 0 times 1 is 0, so you get a 4. 0 times 1 is 0, 1/2 times 1 is 1/2. Now let's analyze this, okay? In the x direction, this is the original point, this is the new point, right? I've gone from 1 to 4, so I've stretched it horizontally times 4, and I've gone from 1 to 1/2 in the y direction, so I've cut it in half. So that seems to be working just fine. The next point that we've been typically dealing with is 4, 0, 0, 1/2, and typically we've been dealing with 2, 1. Let's see what happens with that. And what we will have is 4 times 2 is 8, 0 times 1 is 0, so we get an 8, 0 times 2 is 0, 1/2 times 1 is 1/2. So the point 2, 1 is transformed to this. This x component has been stretched times 4, and the y component again has been cut by 1/2. So in this lesson what we have done is we've kind of broken it down. We want to talk about the concept of a transformation matrix, and that is when we take a point, or equivalently we can talk about vectors also, because kind of the same concept. A point in the plane is really the same as the tip of the vector, right? You typically use these kinds of things a lot in computer graphics. You know, you're trying to rotate, or we're going to talk about rotation very soon, but in this case trying to scale something, make it larger or smaller. You've seen the transformation matrix to make stretch something in the x direction, separately to stretch something in the y direction, and of course you can combine them if you just have the different scale factors in there to do them in the 2 different directions at the same time. The general idea of multiplying by a transformation matrix is going to hold for other things. So very soon we'll be talking about rotating objects and also translating, moving them around. So by putting all of these ideas together, you can take a circle, or let's say a triangle for instance, you can stretch it, make it larger. Later on we'll learn how to rotate that triangle and also move it. And the concept of these ideas is basically how all computer graphics are done. So this matrix math here is used for all of these games and other applications out there in addition to computer graphics, but that certainly is the easiest thing for us to think about. So follow me on to the next section. We will talk about how to rotate objects using a transformation matrix.